This quiz assesses your understanding of the GammaRegressor in Sklearn, focusing on its assumptions about the data it models. I'm testing your knowledge of the gamma distribution and how the GammaRegressor uses it. I present you with a multiple-choice question about the GammaRegressor. You need to identify which statements correctly describe its characteristics and assumptions. I'm setting the stage here. Imagine you are using the GammaRegressor from the Sklearn library to predict the time until an event happens. This sets the context for the quiz question that follows. Think about what the GammaRegressor is doing and what it assumes about the data. The gamma distribution is described here. I'm highlighting key characteristics. It's continuous, meaning its values can take on any value within a range. Always positive. Its values are greater than 0. And right skewed. Its values are more concentrated toward lower values, with a tail extending to the right. Understanding these properties is key to understanding how the GammaRegressor works. I'm summarizing the key features of the gamma distribution in short, descriptive words. Remember these as you tackle the multiple-choice question. These attributes directly relate to the types of data that the GammaRegressor can effectively model. This is one of the options in the multiple-choice question. I'm telling you that the GammaRegressor excels at handling skewed data, which is very common in the real world, especially for datasets where the data is concentrated around certain values. This is another multiple-choice option. I'm stating that a key assumption underlying the GammaRegressor is that the value you're trying to predict, your target variable, must always be a positive number. Here's a multiple-choice option. I'm telling you that the GammaRegressor doesn't assume that the target variable follows a normal distribution. That would be incorrect. This is the final option in the multiple-choice question. I'm indicating that the GammaRegressor does not model the mean and variance separately. Instead, it models the shape and scale parameters of the gamma distribution, and these define the mean and variance. I'm focusing on the assumptions the GammaRegressor makes about your data. It's crucial to understand these because they determine when it's the right tool for the job. We'll explore what data properties make the GammaRegressor a good fit. I see this as a multiple-choice question designed to test your understanding of the GammaRegressor in Sklearn. Let's tackle the options one by one, focusing on the core concepts. We'll check how well you know the underlying math and which scenarios make the GammaRegressor shine. The question asks you to identify the true statements about the assumptions of the GammaRegressor when dealing with a target variable representing the time to an event, like equipment failure. It's important to remember that the GammaRegressor uses the gamma distribution, so understanding that distribution is key. These are the different options that explain the GammaRegressor characteristics. I'll help you evaluate each option to determine which align with how the GammaRegressor works. This is about applying your knowledge of gamma distributions in practice. I see that you're interested in the gamma distribution. It's a continuous probability distribution, which means it describes the probabilities for a variable that can take on any value within a continuous range. It's especially useful for modeling data that is always positive and often skewed to the right, like the time until some event happens. Think of it as a specialized tool for data that's not symmetrical like a bell curve. I understand that the gamma distribution only works with positive numbers. That's because it's designed for things like waiting times or durations, which can't be negative. The gamma distribution is often right skewed. This means most of the data is clustered towards the lower values, and there's a long tail stretching out towards higher values. For example, if you're modeling how long a machine works before it breaks down, most machines might break down relatively quickly, but a few might last much, much longer. That long tail is the skewness. It's like the long tail of the gamma distribution gives a chance to these few high values. This is a multiple-choice question about the assumptions that the GammaRegressor makes. It tests your knowledge of this statistical model. This question asks you to identify the correct statements about the assumptions underlying the GammaRegressor model in Sklearn, a popular machine learning library. The key is understanding the connection between the model and the underlying probability distribution. I'm focusing on what assumptions scikit-learn's GammaRegressor makes about your data. It's crucial to understand these assumptions before you use GammaRegressor for modeling. The GAMMA distribution is like a special tool for handling data. It only works with positive numbers and often shows up when you're looking at things like how long something lasts, like how long a machine works before it breaks. The GAMMA distribution is also usually skewed. This means that one side of the distribution, specifically the right side, has a longer tail than the other. This question tests whether you understand how the GammaRegressor works by focusing on its underlying assumptions. This is true. Because the GAMMA distribution only deals with positive values, the GammaRegressor needs positive data. Think of it this way: you can't have negative time until an event occurs. This is also true. The GAMMA distribution handles skewed data really well. Since many real-world datasets, like time-to-event data, are often skewed, the GammaRegressor is a great choice for these situations. I see that the gamma distribution, which underlies the GammaRegressor, only works with positive numbers. This means any data you feed into a GammaRegressor model must always be greater than 0. Think of things like time until failure. Time can't be negative, right? The gamma distribution is a special type of probability distribution that describes positive-valued random variables, like the time until something happens. It's particularly useful when your data is skewed, meaning it has a long tail on one side. The GammaRegressor, from the scikit-learn library, uses the gamma distribution as its foundation. Understanding the gamma distribution helps you understand what the GammaRegressor assumes about your data. It's crucial to know these assumptions to make sure the model is a good fit for your problem. I'm focusing on the fact that the gamma distribution is often skewed, meaning it's not symmetrical. It often has a long tail to the right, lots of data points clustered near 0, but a few that stretch out to much higher values. This is common when dealing with things like time to failure. You might have many parts failing quickly but a few lasting a long time. I'll explain what assumptions the GammaRegressor makes about your data. It's a crucial part of understanding when to use this statistical model. We're looking at how GammaRegressor uses the gamma distribution to model your data. The gamma distribution is like a special tool in our statistics toolbox. I use it when I'm dealing with positive numbers only, and these numbers often have a long tail on the right, meaning there are a few large values that skew the data. Think of it like modeling the time until something happens. The time can't be negative. This is super important. The gamma distribution only works with numbers greater than 0. If you have data that could be negative, the GammaRegressor won't be a good fit. A right-skewed distribution means most of your values are clustered on the lower end, with a few really high values stretching out the distribution to the right. Think of income. Most people earn a moderate income, but a few very high earners pull the average way up. The gamma distribution is ideal for handling this kind of data. I'm looking at the assumptions behind the GammaRegressor, a machine learning model from scikit-learn. We'll explore what it assumes about the data it's used to model. The gamma distribution, which the GammaRegressor uses, only works with positive numbers. Think of it like this: you can't have negative time until a machine breaks down. That's why the GammaRegressor only works with data points that are greater than 0. The GammaRegressor doesn't directly predict the mean and variance. Instead, it works with two parameters, shape and scale. These parameters define the shape of the gamma distribution, which indirectly determine the mean and variance of your data. It's a bit like building with Legos. You work with the individual bricks, shape and scale, rather than trying to build the whole thing directly. This is the core of our discussion. We are focusing on the GammaRegressor, a statistical model from the scikit-learn machine learning library specifically designed for handling data that follows a gamma distribution. I'll make this clear: the GammaRegressor doesn't directly predict the average, mean, and how spread out the data is, variance. Instead, it works with the shape and scale parameters of the gamma distribution. And these in turn determine the mean and variance. It's like having a secret code. It gives you the key components to indirectly calculate the average and spread. Let's talk about the gamma distribution. It's a special type of probability distribution used for positive numbers. Think about things like time until an event happens. It usually has a long tail, meaning it's likely to be skewed towards the right. Lots of small values and a few very large ones. A skewed distribution means the data is not evenly spread out. In a right-skewed distribution, like the gamma distribution, there's a longer tail to the right. This means most data points are clustered on the left, with a few outliers on the right.